Hello everyone, I'm Jia Yuwang from Tsinghua University. Today, I'm going to introduce our paper, Cosites or Multiple Tables for Feature-Rich and Data-Efficient Machine Learning. Successful machine learning needs to learn from good data. However, one common issue about trained data for machine learning practitioners is the lack of good features. To mitigate this problem, feature augmentation is often employed by enriching features from multiple tables, so as to become feature-rich machine learning. For example, consider a machine learning task that predicts the score value of a movie based on features such as movie ID, title, length, and box office. Intuitively, because many important features are missing, such as the features of directors of a movie, it is hard to train a good machine learning model. Fortunately, we can augment the features of movie with other four tables. The feature-rich table with new features augmented through joins, denoted by movie plus, is shown in the red figure. With feature-rich machine learning, the trained model can achieve better accuracy. Data-efficient machine learning aims to improve training efficiency. Generally speaking, there are two aspects to do such acceleration. From the algorithm perspective, we can use SGD to improve the training efficiency. We can also do this from the data perspective. That is, we can accelerate by reducing the number of training items, and intuitively, the efficiency will be improved, which is the concept of the cosite. There are many recent efforts on selecting a trained data subset that can theoretically and practically perform on par with the full dataset. Note that the two perspectives are orthogonal and complementary. That is, we can run SGD on the cosite. In order to achieve both feature-rich and data-efficient machine learning, an intuitive solution is to first conduct feature augmentation through joins across multiple relational tables, followed by performing cosite selection over the trained data with enriched features. Before we discuss the problem we studied in the paper, let's analyze the benefits and limitations of the aforementioned strategies using real experiments. The first choice is training with the base table. If we train a machine learning model using the base table T for a multi-classification task, the accuracy is relatively low, and it uses 11 minutes for training. Secondly, if we first compute the cosite of the base table, and then train a machine learning model using the computed cosite, we can also achieve a similar accuracy, but use 2 minutes in total for selecting the cosite and training with the cosite. This shows that using cosite can significantly reduce the training time without sacrificing the accuracy. Besides, we can also train with the augmented table or the cosite of the augmented table. These are shown as method 3 and method 4 in this page. We can observe that auto training with the augmented table can achieve a much higher accuracy. It takes a much longer time, because as we know, the process of feature augmentation consists of one-to-many or many-to-many joins. Therefore, the size of the augmented table is likely to be much larger than the base table. This example tells us that the feature augmentation can significantly increase the accuracy, and training with the cosite can significantly reduce the time. However, computing the cosite over a large table, for example, the augmented table, is time-consuming. Therefore, in order to efficiently compute the cosite of the augmented table, the problem we aim to tackle is whether we can compute the cosite of the augmented table without join materialization. To dive into this problem, let's first analyze how the cosite is selected for a single table. Most machine learning models use gradient design to train, and we have to compute the sum of gradients over all training items. So the gradient-based cosite selection is to select a subset of the full, such that the cosite gradient is as close to as possible to the full gradient. That is, minimizing the gradient approximation error, since the cosite is a subset of the full. How can we make the cosine gradient equal to the full gradient? The answer is that we assign a weight on each individual example. Let us use an example of the cosine selection. The left one is the full train side, and the right one is the cosine, which includes 3 tuples and are associated with 2 mappings. The first mapping gamma is simple. For example, gamma 2 equals 4 indicates that the second item in coset C is the fourth one in original table T. The second mapping phi is important. It shows that tuple I in T is represented by tuple J in C, and the weight of tuple I in C equals to the number of tuples in T that points to tuple I. In this example, suppose that similar colors indicate similar gradients. Current coset C is a good coset. The reason is that each color of tuples in T are represented by a very similar tuple in C. The weight of the 3 tuples are 3, 2, 3 respectively, and then the gradient approximation error is minimized, close to 0. Therefore, coset selection is to select a subset with a fixed size, such as well as the mappings, which determines the weights. The basic cosine algorithm is illustrated in the figure. Initialized with an empty coset C, a coset of size k is achieved using 3 nested for loops. Each iteration of the first for loop will add tuple with the maximum utility to the coset. The utility of a tuple denotes the reduction of gradient approximation error after adding the tuple into the coset. Each iteration of the second iteration will compute the utility of a tuple T that is not in the coset. In the third for loop, it iterates all tuples in T to compute the utility of the tuple being measured in the second for loop. Finally, it computes the weight of each tuple in the coset, which will be used to approximate the full gradient. Apparently, the solution with 3 loops is rather time-consuming. Fortunately, cosines satisfy the submodular property. Based on this property, an efficient method can accelerate the second for loop that uniformly samples the tuple set S and selects the best one from sampled ones. With sampling, it still holds a relatively good approximation ratio. Now, let's come to coset of multiple tables, which is the scenario in feature-rich machine learning. As we have mentioned, a natural solution is first to do feature augmentation by executing the joins, and then use the above coset selection on the materialized result. However, since the materialized view might be very large, the efficiency of coset selection is low. To solve this problem, our key idea is to estimate the utility of each group without joint materialization. Here, a group refers to a set of tuples in the joined results that have the same attribute values on a predefined set of attributes. Conceptually, the utility can be estimated by first computing the feature similarity of tuples in each individual table, and then aggregating them using a dynamic programming algorithm without joint materialization. By doing so, we can significantly reduce the computation in the third for loop, thus improving the overall efficiency. Our solution is inspired by the classical SQL query optimization technique pushdown that moves predicates in the where clause closer to the tables they refer to. In our context, pushdown for coset over multiple tables means that we can approximately compute the gradient of each individual table and sum up its gradients from multiple tables to compute the full gradient. That is, the gradient computation is pushed down. Next, we'll prove that the full gradient can be bounded using partial feature similarity values in each individual tables of different groups. Firstly, using the definition of weights, we have this equation. We can then use this equation to first transform the gradient approximation error like this. After that, we can apply triangle inequality. Recap from the aforementioned example. Intuitively, the right hand will be minimized when the mapping file is set to assign each tuple in T-class to the closest tuple in the call site with regard to the gradient. So the right hand can actually be rewritten as this. After that, by leveraging max-min inequality, we can get the following expression. Furthermore, from convex problem, there is a theorem that the gradient difference can be bounded by the Euclidean difference between feature vectors. Therefore, we can conclude that the gradient approximation error can be bounded independent of the optimization problem in practice. Thus, we come to this result. Finally, we get the following bound, and minimizing the error becomes to maximizing this value. This expression actually denotes the call site score, and we want to select the call site with a maximal score. In our paper, we proved that this problem is NP-hard, and we also proved that this problem also has the submodular property, so we can also use the aforementioned sampling optimization. We will next describe the proposed algorithm for this problem. The proposed method can compute this similarity efficiently, thus reducing the call site selection time. Here is an overview of our proposed recon algorithm. It accelerates the computation in the third for loop. To obtain such acceleration, it first precomputes the feature similarity in each individual table. After that, during the call site selection, the feature similarity computation can be accelerated by simply aggregating these partial results. The reason we can precompute the partial feature similarity is that each feature vector in T class can be represented by the concatenation of subvectors from different tables. Intuitively, to capture the feature difference in T class, we can first compute the partial feature similarity inside each table. Hence, we push down the computation to each individual table as a precomputation step. To be specific, for each table, the feature vector difference of any tuple pair is computed. Then, given the joint tree, group K, and precomputation results, the feature similarity in T class can be computed by aggregating the results in each table without materializing T class. To this end, we propose a dynamic programming algorithm to efficiently compute the feature similarity between each group and each tuple in the call site. For more details, please refer to our paper. For experiment, we used 5 real-world datasets that covered various data characteristics and machine learning tasks to verify the performance of Recon. For effectiveness, we showed the test performance on different datasets for different baselines and Recon. We can observe that Recon almost has the same accuracy as using full data. This can because Recon can well approximate the full gradient accurately with theoretical guarantees. Meanwhile, the size of the selected call site is less than 1% of the size of the full data. For efficiency, we show the total time including both call site selection and model training for different baselines and Recon. We can see that, in general, Recon achieved an efficiency improvement of nearly 2 orders of magnitude compared with full. We also conducted experiments of varying call site size. This figure shows the training loss for different baselines. We can see that Recon converges to almost the same loss as full, which demonstrates that Recon can accurately estimate the gradient with theoretical guarantees, and thus achieve the same performance as the full data. Finally, to summarize, in this paper, we propose Recon, an algorithm that can efficiently select call site over relational data. We have made the code available on GitHub. If you have any questions, feel free to ask. Thank you.